When we think about the Milky Way galaxy, we usually imagine stars, planets, nebulae, and clouds of gas and dust. But there is another major component of our galaxy that cannot be seen with ordinary telescopes and is often overlooked in popular discussions. This component is the Milky Way's magnetic field. Magnetic fields exist throughout the universe. They are present around planets, stars, and entire galaxies. In the Milky Way, the magnetic field plays an important role in shaping how gas moves, how stars form, and how energetic particles travel through space. Despite its importance, mapping the structure of the galaxy's magnetic field has been extremely difficult. Recently, a team of Canadian researchers announced a major step forward.
If you enjoy deep-dive science documentaries like this, focused on real data, real mysteries, and the edges of human knowledge, consider subscribing. New videos explore the universe where certainty ends and discovery begins. And let us know in the comments what you think. Thanks for watching.
Using radio observations collected over many years, they produced one of the most detailed large-scale maps of the Milky Way's magnetic field ever created, especially across the northern sky. This work gives scientists a much clearer picture of how magnetism is organized across our galaxy and how it interacts with interstellar matter. In this video, we'll explain what the Milky Way's magnetic field is, why it matters, how Canadian researchers mapped it, and what this new map helps scientists understand about the galaxy we live in. A magnetic field is a region of space where magnetic forces influence charged particles. On Earth, the magnetic field guides compasses and helps protect the planet from solar radiation. In space, magnetic fields are much larger and weaker, but they still have important effects. The Milky Way's magnetic field stretches across tens of thousands of light years. It threads through clouds of gas and dust known as the interstellar medium. Although the field is very weak compared to a refrigerator magnet, it affects enormous amounts of matter over vast distances. The galaxy's magnetic field is thought to follow the spiral structure of the Milky Way, but not perfectly. In some regions, it appears ordered and smooth, while in others it becomes tangled and chaotic. Understanding this structure is important because magnetism influences many galactic processes. For example, magnetic fields can slow down the collapse of gas clouds, affecting when and where new stars form. They guide the motion of cosmic rays, which are high-energy particles traveling near the speed of light. They also interact with shock waves from supernova explosions, shaping the structure of interstellar space. Despite these effects, magnetic fields do not emit light on their own. That makes them difficult to observe directly. One major challenge in studying the Milky Way is that we are inside it. Unlike other galaxies which we can observe from the outside, our view of the Milky Way is limited by our position within its disk. Dust blocks visible light, and the galaxy's structure appears flattened across the sky. Mapping the magnetic field adds another layer of difficulty. Astronomers cannot simply take a picture of magnetism. Instead, they must infer the presence and direction of magnetic fields by observing how they affect light and radio waves traveling through space. Previous maps of the Milky Way existed, but they were often incomplete or limited to certain regions of the sky. Many relied on sparse data or observations at a single frequency, making it hard to separate overlapping magnetic structures at different distances. The new work by Canadian researchers addresses these limitations by combining wide-frequency radio observations with advanced analysis techniques. The new map comes from a long-term project called the Global Magneto-Ionic Medium Survey, or GMIMS. This is an international effort, but Canadian institutions have played a leading role.
GMIMS focuses on studying the magnetized interstellar medium using radio waves. Radio waves are especially useful because they can travel long distances through gas and dust without being blocked. The survey uses data from several radio telescopes, including the Dominion Radio Astrophysical Observatory, or DRAO, in British Columbia. Over many years, astronomers collected radio signals from across the northern sky, covering a wide range of frequencies. This wide frequency coverage is crucial. It allows scientists to analyze how radio waves change as they pass through magnetized plasma in the galaxy. To understand how this mapping works, it helps to explain a phenomenon called Faraday rotation. When polarized radio waves travel through a region of ionized gas that contains a magnetic field, the plane of polarization rotates. The amount of rotation depends on several factors: the strength of the magnetic field, the density of electrons, and the distance the radio wave travels through that region. By measuring how much the polarization changes at different frequencies, astronomers can infer information about the magnetic field along the line of sight. This technique does not give a simple picture of magnetism in one step. Instead, it provides layered information, with contributions from different regions of the galaxy overlapping in complex ways. Separating those layers requires careful data processing and modeling. The Canadian researchers used a method called rotation measure synthesis. This technique allows scientists to disentangle magnetic structures at different distances, creating a three-dimensional view of magnetism across the sky. The resulting map is one of the most detailed, large-scale representations of the Milky Way's magnetic field ever produced. One key result is that the field is far more complex than simple models suggested. Instead of being a single, smooth structure following the spiral arms, the field shows variations in direction, strength, and coherence across different regions. In some areas, the magnetic field appears well-ordered over large distances. In others, it becomes tangled, possibly due to turbulence, shock waves, or interactions with supernova remnants. The map also reveals multiple layers of magnetic structure along the same line of sight. This confirms that the interstellar medium is not uniform, but contains overlapping regions shaped by different physical processes. Importantly, the survey provides a consistent view across the northern sky, allowing astronomers to compare regions directly rather than relying on separate studies with different methods. One of the main reasons scientists care about galactic magnetic fields is their role in star formation. Stars form when clouds of gas collapse under gravity. However, magnetic fields can resist this collapse by providing additional pressure. In some cases, they slow down star formation. In others, they help channel gas into filaments that eventually form stars. The new magnetic field map helps researchers understand how magnetism interacts with gas on large scales. By comparing magnetic structures with known star-forming regions, scientists can test theories about how stars form and why some regions of the galaxy are more active than others. This is especially important for understanding the Milky Way's history, since star formation rates have changed over billions of years. Another area affected by galactic magnetism is the movement of cosmic rays. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at near light speeds. Their paths are strongly influenced by magnetic fields, which bend and scatter them. Without accurate maps of the Milky Way's magnetic field, it is difficult to trace where cosmic rays come from or how they propagate through the galaxy.
The new map provides valuable constraints for models of cosmic ray transport. This helps researchers better understand the sources of these particles, such as supernova remnants, and how they spread energy throughout the galaxy. Magnetic fields are not static. They evolve over time, shaped by processes like turbulence, rotation, and star formation. Understanding their structure helps scientists learn how galaxies evolve. The Milky Way's magnetic field is thought to be maintained by a dynamo process, where the motion of ionized gas amplifies and organizes magnetic fields over long periods. Observations like those from GIMIS provide real data that can be compared with theoretical models of galactic dynamos. By studying the structure and variations of the magnetic field, scientists can test whether current models accurately describe how galaxies maintain magnetism over billions of years. Earlier studies of the Milky Way's magnetic field often relied on limited datasets or indirect tracers, such as starlight polarization or observations of individual objects like pulsars. While valuable, these methods could not easily produce a continuous large-scale picture. The GIMIS-based map improves on this by offering uniform coverage and consistent analysis across a wide area of the sky. This does not mean the map is final or complete. It represents a major step forward, but future surveys, especially in the southern sky, will further refine our understanding. Upcoming radio observatories, including the Square Kilometre Array, are expected to provide even more detailed data, building on the foundation laid by this work. Canada has a long history of contributions to radio astronomy, and this project highlights that role.
Institutions such as the Dominion Radio Astrophysical Observatory have been central to collecting high-quality radio data. Canadian scientists also played key roles in designing the survey, developing analysis methods, and interpreting the results. This research demonstrates how long-term investment in scientific infrastructure can lead to breakthroughs that benefit the global scientific community. The new magnetic field map is not an endpoint. Researchers will use it as a reference for many future studies. One goal is to combine this magnetic data with observations of gas, dust, and stars to create more complete models of the Milky Way. Another is to study how magnetic structures relate to specific features, such as spiral arms or supernova remnants. Scientists are also interested in comparing the Milky Way's magnetic field to other galaxies. This helps determine whether our galaxy is typical or unusual in its magnetic behavior. As more data become available, especially from next-generation radio telescopes, these maps will become more detailed and extend across the entire sky. The new map of the Milky Way's magnetic field created by Canadian researchers represents a major advance in our understanding of the galaxy. By using radio observations and advanced analysis techniques, scientists have revealed complex magnetic structures that influence star formation, cosmic rays, and the overall evolution of the Milky Way. Although magnetic fields remain invisible to our eyes, studies like this show that they are a fundamental part of the galaxy's structure. Mapping them helps complete the picture of how the Milky Way works as a dynamic system. This research also highlights the importance of long-term scientific collaboration and careful observation. As astronomers continue to refine these maps, we can expect even deeper insights into the hidden forces shaping our galaxy.